Now that we have seen that the atom is made up of three basic subatomic particles, the proton and neutron that resides in the nucleus, and the electron moving about this nucleus within specific electron clouds, or what we call orbitals, let's consider the mass relationship that exists between all of these three. To do this correctly, let's start by defining the following terms: the atomic number, the mass number, and a phenomenon called isotopy. The atomic number Z is a count of the number of protons in the nucleus of an atom. The number of protons present in the nucleus tells us what type of element that atom is. By default, the number of protons and electrons in an atom balances out. This is why an atom is said to be electrically neutral. But a net charge is generated when the atom gains extra electrons or gives out electrons. Let's consider this atom for example. Imagine it gives out an electron. It will have a net charge of +1 because the number of positively charged protons is now more than the negatively charged electrons by exactly 1, which is the exact amount of electron it gave out. If an atom gains electron, its net charge becomes -1, since there are now more electrons in the atom than proton by 1 unit. Atoms with net positive charges are called cations, while those with net negative charges are called anions. Now that you understand the atomic number, let's move on to the next, the mass number. What is the mass number? The mass number is a count of both number of protons and also the number of neutrons in the nucleus of the atom. It is denoted by the letter A. Therefore, mass number A equals number of protons plus number of neutrons. If you have been observant, you would have recognized that we have not given either the mass number or atomic number any units. You know why? Because it's just a numerical count of how many subatomic particles are in the atom. Same way you can make a count of number of buckets in your house. This number doesn't tell you how much mass the bucket has. Rather, it tells you about how many you have. The reason for this analogy is because oftentimes people confuse mass number for atomic mass. Maybe because they both contain the word mass. While mass number deals with just counting how many protons and neutrons are in the atom, the atomic mass care about what those will weigh on a scale. We will talk more about this later. Sometimes, when we compare two atoms of same element, we see that both have same atomic number but different mass number. The number of protons in both atoms is the same. Of course, that's why they are of the same element. But the number of neutrons in their atoms are not the same. This is why they have different mass number. In chemistry, there's a name for such a phenomenon. We call it isotopy. And we call such atoms isotopes. Examples of atoms exhibiting isotopy would be hydrogen, oxygen, carbon, and so on. Isotopes are named using their mass number. So for carbon has 6 protons and 6 neutrons. This means any atom that has 6 protons would be a carbon. But we also know that there are carbon atoms with more than 6 neutrons. Recall our definition for isotopy: a situation in which atoms of same element have same atomic number and different mass number. So carbon with 6 protons and 6 neutrons, we have a mass number A as 12. Carbon with 7 neutrons, we have mass number as 13. While carbon with 8 neutrons, we have mass number as 14. All of these 3 carbons are isotopes and are called according to their mass number: carbon 12, carbon 13, and carbon 14 respectively. The correct way to denote the atomic number and mass number of an atom, say X, is this, where A is the mass number and Z is the atomic number. We will revisit this concept when we start calculating average atomic masses later on. The subatomic particles weigh something, albeit little. Other than the neutron, which has no charge, the proton and the electron do have charges. Let's have a look at the mass and charges of the subatomic particles. So this table shows the masses and magnitude of charges of the subatomic particles. You'll quickly notice how small they are, especially the mass of the electron. This is one reason its mass is not considered when calculating the mass of the atom. The neutron is just slightly heavier than the proton. While the proton has a charge unit of 1, the electron has an opposite charge unit of -1. The neutron has no charge. Let's use this question to explain a few more things for you. Give the number of protons, neutrons, and electrons in each of the following species: boron 11, mercury 199, and mercury 200. To figure this out, I will start by making a table and give headings like this respectively. For boron 11, from the isotopic notation, you see the mass number as 11 and atomic number as 5. This is easy and straightforward as you've been given everything you need to compute the solution to these questions asked of you. Since atomic number equals number of protons, I'm safe to say that the proton is 5. Since the boron is not an ion but rather a neutral atom, its number of protons will be equal to the number of electrons. Thus, our electrons here would also be 5. The mass number is the sum of protons and neutrons in the nucleus of the atom. As given, the mass number is 11. We know the atomic number or number of protons to be 5. To get the number of neutrons, we do simple arithmetic. This will give us 6. I'll leave you to try out the remaining questions. Yes? No? Would you love me to solve them for you? Okay, I would. I'll solve one and leave the other one for you. Just put in the solution in the comment section. Mercury 200 simply means mercury has a mass number of 200. Its atomic number is 80. This means its number of protons is 80. Since the mercury is not an ion, its number of protons are equal to the number of electrons, which is 80. The number of neutrons can be gotten as before. Did you observe something between both mercury atoms? Take a close look. You will see they both have same atomic number but different mass number. What did we call such atoms? Yeah, isotopes. Like I told you earlier, that we will visit the concept of atomic mass in full. So here we are. The atomic mass is the quantity of matter contained in an atom of an element. In the lab, as difficult as it seems, a single carbon-12 atom was isolated and weighed. The value in grams gotten was super small. 1.992646547 times 10 to the negative 23rd gram. This value was then divided into 12. The reason for this is that we know that a carbon-12 atom has 6 protons and 6 neutrons. So we are trying to share that mass among the protons and the neutrons. Given that the mass of the electron is super negligible, we most times disregard its mass. This is the same thing you do when you are trying to know your weight on a scale. You don't take off your necklace because you know it will add little or nothing to your mass. After dividing the mass by 12, the value gotten was 1.661 times 10 to the negative 24th gram. Since the mass of the whole carbon-12 atom has been divided by 12 to get 1.661 times 10 to the negative 24th grams, it follows logic that one unit that constitutes the mass of the carbon atom will weigh this value, be it a proton or a neutron. For ease of writing and doing numerical calculations in the lab, scientists came up with a scale of measuring masses of atoms with respect to the carbon-12 weighing system. Scientists called each proton and neutron an atomic unit. So carbon-12 will have 12 atomic units instead of writing 1.661 times 10 to the negative 24 grams times 12, which would give us the initial value of 1.999 blah blah blah, which was weighed in the experiment. So let's say I want to weigh nitrogen, for example. Instead of going to the lab to do the experiment and get the mass of a nitrogen atom in grams, I'll just use a reference scale instead, which is the carbon-12 scale. I will ask myself, how many atomic units of carbon-12 will balance out a nitrogen atom if I add them on some sort of scale of a seesaw? A quick way to find the atomic mass of a given atom under the carbon-12 scale, just add up the numbers of the protons and the neutrons together and end it with AMU. It is important you understand that AMU is not the same thing as grams. AMU is a relative scale, not the actual value of the mass in grams. One question that always gets asked when we discuss atomic masses of atoms is, why is the atomic mass of an atom slightly less than the sum of its individual subatomic particles? What this means is that if you could rip off the subatomic particles and weigh them separately, then compare them to what an atom containing that same number of particles weigh, you'd find that the mass of the atom is slightly less than the sum of its subatomic particles. The reason for this mass defect is that some of the mass of the atom has been converted into binding energy that binds the particles of the atom together. Now let's talk about what the average atomic mass is. The average atomic mass is a weighted average of all isotopes of that element. What does this mean? I know if I ask you to calculate the average of a set of numbers, say 1, 2, 3, and 4, for instance, you will just add them up and divide by their total number. Weighted averages are a bit different in that it accounts for percentage abundance. Using this concept, to calculate the average atomic mass of each individual isotope is multiplied by their percentage abundance and then summed together. Let's take a quick look at an example. Copper, a metal known since ancient times, is used in electrical cables and pennies, among other things. The atomic masses of its two stable isotopes, which are copper 63 and copper 65, are 69.09% and 30.91% respectively. They have atomic masses of 62.93 AMU and 64.9278 AMU respectively also. Calculate the average atomic mass of copper. To calculate the average atomic mass of each individual isotope is multiplied by their percentage abundance and then summed together. The value gotten is then divided by 100. So let's work out this example.